Okay, and then in
Is it visible
reading
now?
reading mode, maybe
Yeah, I would do that.
either full screen or
Just
reading mode.
Control L.
Okay, I think we're all set.
Okay.
So, shall I introduce the speaker?
Yes, please.
Are you, have you started the recording?
Yes.
Okay, so it's a pleasure for me to today to introduce the speaker of this seminar, Special Functions and Number Theory. The speaker is Abdulhafeez Abdulsalam from Nigeria. He did his bachelor degree in Nigeria and is at the moment studying at ICTP in Trieste in a very prestigious program for talented students. And he is talking about his own research about integral evaluations and formulas. And his talk will be about Fourier sine and cosine transforms of expressions with nested square roots. Yeah, please go ahead.
Okay, thank you for the introduction. So it's nice to meet everyone. So I would be talking on Fourier sine and cosine transforms of expressions with nested square roots. So, and the choice of the topic stemmed from the results that were obtained. So, okay. So just as a few notion of acknowledgements, I would like to express my gratitude to the organizers of the seminar, Gaurav Bhatnagar from Ashoka University, Atul Dixit from IIT, Krishnan Rajkumar from JNU in New Delhi, and Michael Schlosser from University of Vienna in Austria. So thank you very much for this invitation. So the talk would cover two parts. So I divided it into two parts. The first part is the algebra part, or we would say it's just on integral transforms with applications from algebra. So in simplifying the closed forms that would appear. So we would need the solution to the Pythagorean equation here. So which is this for m and n integers. So, and the other one would be on integral transforms. So just as a brief story of how the work began, it started as an observation that the Gaussian integral is solvable okay, hold on. Like I could also write. So the Gaussian integral is solvable by the Laplace transform. So that's the first part of the paper. It's just a brief explanation of how one could solve the Gaussian integral, which is just the integral from negative infinity to positive infinity of exponential minus x squared. So one could also use Laplace transform to solve that. So, and I checked some papers before starting the work, and I saw that this author, this Appelblatt in 1994, used Laplace transforms to evaluate some definite integrals with logarithmic integrands. So I would say his is actually more technical than other papers that I saw on this application of Laplace transform. So, and then you would find this also on the web. Gordon and Stewart also used it to compute improper integrals. So before this presentation, I had some discussions with my supervisor here, who would be supervising my project. So Emmanuel Canero at ICTP. So he advised that I check some of these integrals if they do appear in the famous Grashstein and Reisig. Yeah. So I did so, and I realized that two of the results were actually two results in the bunch of results that were obtained were actually in Grashstein and Reisig. And I try to check the origin of those integrals. They are just two integrals, but it couldn't lead me anywhere because I keep going back and back in history, but I never did get a touch of where the proof for those two integrals were. So just as a remark. So yeah, the definitions here. So I would just be using the Laplace transform, which is very famous. So it's just this integral. And then the inverse Laplace transform is given by this integral. So which is rather technical, I would say, because it's the Bromwich integral. So one could use this to evaluate the inverse Laplace transform of a function. So for these values, for the real part of a, c greater than 0, and this here, we study three main integrals in the work. So which are these integrals? And they are related to one another. So for instance, one could observe here that if you differentiate with respect to b, if you differentiate this integrand with respect to b, you would obtain this integrand here. So, and this integrand here is related by replacing b here with bx squared and replacing b here with bx and multiplying this integrand by x. So at b equals 0, one would observe that this would be cosine of 0, which is 1. So, and we would just get the Gaussian integral. So one could actually look at this integral as some form of generalization of the Gaussian integral. So if you let these symbols represent those three integrands, then we would observe these relationships. As I have said earlier, this is the derivative of the first here, and when you replace this b here with bx, here, when you replace this with bx, and you replace the x here with x squared, and then you multiply with an x, so you get this relationship. Okay, so yeah, so we observed from the results that the results were also connected to the error function, and the error function is defined by this integrand here. The complementary error function is just 1 minus the error function. And when we use these solutions to the Pythagorean equation in the closed form for I2, so which was the second integral we defined earlier, the one with the sign. So we would observe that we could derive some integral representation for the error function. So, and this is just one of the integral representations that one would be able to derive from the closed form for the I2 integral that we defined earlier. So we also need the definitions of the cosine and sine transform. So this is the Fourier cosine transform, or Fourier, as some people would pronounce. So this is the Fourier cosine transform. It's just this integral here. You have this f of a, then you multiply with cosine of ax. So this is this integral with some conditions, of course, attached to the function f of x. So the Fourier sine transform is defined by just replacing the cosine here with the sine. And then you have the Mellin transform, which is just some discretized version of the Laplace transform. So resulting Fourier cosine and sine transforms. So as I said earlier, the choice of the topic was as a result of the results that were obtained. So this is one of them. So one would obtain this result for this Fourier cosine transform. So a and b here are free variables. Then you are just integrating over x. So you would get the result in terms of c here because it's integrating with cosine cx multiplied with the function, we multiplied with this function. So our result would be in terms of A, B, and C. And this is an example of a Fourier sine transform that was obtained in the result. So, and why I chose the, oh, sorry, why I chose the topic to be Fourier sine and cosine transforms of expressions with nested square roots is because we can observe that this expression contains a square root inside a big square root here. So in that way, I just called it nested. So we also obtained some transform-based identity. So it's this integral here. We have this integral identity is valid. So provided that these two integrals exist. So, and then we impose some condition. This symbol here means the imaginary part of gix. And this is just I here, which is just the square root of -1. And this is the real part here. So we impose some conditions on this function here, this imaginary part of gix, because it's the only important function in this integral. This is x here, then you just need a condition on this. And the condition is that this imaginary part of g of ix here is absolutely and square integrable on 0 to infinity. What this means is that the integral on this function from 0 to the absolute value of this integral from 0 to infinity of this function is finite. That's for absolutely integrable. And for square integrable, you just raise this to power 2 here. That's just the condition imposed on the imaginary part of g of ix. And then we would obtain this corollary here by making use of a suitable function here. By making the choice of a suitable function here, one would obtain this very nice result here. So this work was done in collaboration with an Iraqi undergraduate student, so whose name is Ammar Muhammad. So I saw one of the integrals he evaluated, and I was quite grasped by it, and I chose to do some more difficult ones. So, and then I invited him, and then we collaborated on the work all together. So this was what I saw from Ammar. He evaluated this integral here. The proof is rather short. One could define this integral here. So replacing b with ab here, one can define this integral like this and call this integral f of ab. So evaluating the Laplace transform of f of ab, which is just multiplying the function by exponential minus as and integrating over a, one would obtain this here. So it's rather simple because when one does that here, it's just multiplication with exponential minus as and then integrating over a. So one would switch the order of integration by Fubini's theorem. So because the integral is absolutely convergent, one can switch. It's non-negative and absolutely convergent here. So one can switch the order of integration here. So one would just have this to be s plus x multiplied with a, and then the a. So one would consider this integral here. So it's just the Laplace transform of sine x. We just need to know that. And the Laplace transform of sine ax is just a over s squared plus a squared. So it's quite elementary in that sense. Okay. Should erase this. Okay. So evaluating the Laplace transform of f of ab with respect to a, one would obtain this. As I said earlier, we only need to know the Laplace transform of the sine function to get this result here. So the bulk of the work would just be in evaluating this integral here. So one could just cancel out this here, and one would be left with square root of x in the numerator, and one could just replace x with u squared here, and one would arrive at this equation. Sorry, at this expression rather. So one would arrive here. It's not so easy to arrive here, or rather, it's not so easy to evaluate the integral here from here, but this is just expansion here. So, and one would need to evaluate this integral, we would just need to expand in this way, x squared plus a, x squared plus b, and do partial fractions. Then one could integrate to get the arctan function and then arrive at this result. So it's not so difficult. The one after this is a bit complicated. So, but then I will just give the necessary details. So evaluating the Laplace transform, we arrive at this result here. Then we just need to take the inverse Laplace transform of the result here. And we need to know that the Laplace transform, we need to recall that the Laplace transform of, so we need to recall that the Laplace transform of a to the power s exponential as or exponential minus as. Maybe I could call this n. You could just choose whatever variable you want. Maybe I call this t minus 1 or n minus 1. So one would recall that this is just n factorial over let me use t here, which is quite familiar. People are quite familiar. So this would be t here, and this would be t to the power n minus 1. So using this t one here, one would have s plus a here to the power of n here. Okay, this would be gamma n plus 1 here. Oh, here, n minus 1 factorial. So sorry, it's been long. I used to. Yeah, so this is like n minus 1 factorial here. So if one puts 1 here, one would have 1 over s plus a to the power of 1. So 1 over s plus a. Yeah, so this is correct. So one could use this here to evaluate the inverse Laplace transform and obtain the result. So the next integral would be a bit complicated. So I just decided to replace the choice of function of the sine here with the cos. That was the I1, I believe, that was considered. But before that, we could just look at some examples here. So for A equals 3, B equals 4, and C equals 1. So one has this integral, one would obtain these results here. So these are examples. And one other thing one could notice that from here, one could just differentiate with respect to B, with respect to A, and obtain even nicer results. So, and which is listed in this example, in these examples. So these are 3 examples. This is differentiation with respect to B, and this is differentiation with respect to A. So one would obtain these examples. So this is the next integral here that is considered. So this is the one that appears in Grashstein and Reisig. So one would have this result, and one could view this as a Fourier sine transform by just multiplying by √2 over pi. It's a Fourier sine transform. So to prove this result here, we are going to consider this integral on its own and reduce it to the I3 that was just previously evaluated. So with this substitution, one would get this here by replacing x with AU. One would have this. And then this substitution here would give this result. And then one last substitution would yield this result here. And one could just view this as a version of what we just proved, because we proved the one, if you could remember, it's just with square root of x here. This was just x, and this was a b, and there was an a here. So one would just use that, just substituting, just replacing the b with the 2a and just making those suitable replacements, one would get this result here. So this Fourier sine transform here, I tried visualizing it. And this is just how the integrand looks for a equals 1, b, and b equals 1, and c for c equals 3. So this is how the integrand looks. And then this is the transform result as a function of c. So one would obtain this here. So here I used the solutions to the Pythagorean equation. So by replacing b with this alpha squared minus beta squared, c with 2 alpha beta, and a with alpha in the previous theorem, one would obtain this result. So, and it's a bit nice because one could see that this is alpha times alpha squared plus beta squared. You have alpha squared plus beta squared in the denominator, and here you have beta. So you could ask, why not alpha over alpha squared plus beta squared with this exponential? And one would see that that's actually the result with the cosine version of this identity. So we would get there. So here we just have it in this way, but in the cosine version, it's alpha over alpha squared plus beta squared exponential minus this. So this is what the solution to the Pythagorean equation does to the integral that we just proved earlier on. So we would get this nice result. For example, if you replace alpha with 2 and the beta with 1, one would obtain this integral. So the closed form for I1. So I arranged the integrals, the proof of these integrals in the order of their simplicity. So I arranged it in 3, 1, 2. So we just did one. We've done 3. And from 3, we derived a Fourier sine transform. So now we are going to consider I1 here, which is the one with the cosine. Yeah. So this one is like this. When you integrate this function, you have this result. So similarly, one would just, okay, and if one replaces a with p squared minus q squared, these are just the solutions to the Pythagorean equation. So one would get this result here. So this whole expression would reduce to this with the solution to the Pythagorean equation. So we could just consider this integral here with b replaced with ab. So, and the reason for doing this is the same reason for doing the first one. It is for evaluating the Laplace transform, because we cannot just, if you multiply here with exponential minus a, then there is no a term here. So it's like an empty, it's like something that is empty. So you just need to make some replacement of b here with ab. And at the end of the result, one could replace b with b over a. So evaluating the Laplace transform of this integral here, which is this function, one would obtain this result here. So to obtain this result is rather complicated, and the proof was given in the appendix of the paper, because I had to make some weird expansions and some weird partial fractions. So it was the most complicated Laplace transform to evaluate in the paper, and it was the longest. So one would obtain this result here. So, and taking the inverse Laplace transform, so one would just do as we did earlier. So by recalling that the Laplace transform of, so using this a variable, so you would just replace the exponent with half. So you would have half minus 1. So which is we discussed a to the power n minus 1 times a to the power, or t to the power n minus 1 times exponential minus 80. So recalling that Laplace transform, which is very elementary. So one could just evaluate the inverse Laplace transform. So all of these are just constants here. So this is the bulk of the problem, and one will just have this result here. So as we said earlier, to complete the proof, one would just need to replace this B here with B over A, and then we would get this result here. So the next step, or the next thing to do ideally, would be to reduce this to a Fourier cosine transform. So the substitutions were meant to reduce all of these, to reduce this expression inside the cosine, inside the cosine function here, to just cosine of a constant times x. So, and the substitution are a bit similar. But before that, I will just list a few examples here. So this is the first one here. For a equals 3, b equals 4, and c equals 1, we would have this result. And this is the result of a derivative. So as I said earlier, the beauty of this work is that when one derives one integral here, one could keep differentiating to obtain very nice results. So you could differentiate with respect to b. So that is, one could bring in the partial derivative in, because this integral is absolutely convergent. So one could bring in the partial derivative and take the derivative here. And one could keep doing that. But the more you differentiate, the more the complication arises, because it's not easy to differentiate this stuff. And even using Mathematica would be stressed at some point. So one would just have this. This is the first one with the derivative with respect to b, and this is the derivative with respect to a. And this is the derivative with respect to c. So with these substituted variables. So here, as I said, ideally we would want to reduce that cosine of that function to just cosine of a constant times x. So, and how to do that is just by making substitutions similar to the ones we made earlier. So I skipped that because the substitutions are similar. So then we would have this corollary here. So as I said earlier, or as I gave a spoiler, so we would see this is alpha over alpha squared plus beta squared times the exponential of minus alpha times alpha squared plus beta squared here. So I found this result very nice, because you just have this fraction here and you have it multiplied by the exponent, the negative exponent of the product of the numerator and the denominator. So, and this is just, as we did earlier also, this is just a substitution of the solutions to the Pythagorean equation. So one would just substitute a to be alpha squared minus beta squared, b to be 2 alpha beta, and one would arrive at this very nice result. So closed form for I2. So we've done I3, we've done I1. So the next thing to do, or the next thing we are considering, is I2. So this is the integral here, and it involves the error function. Why it involves the error function is because at some point in the proof, to evaluate the inverse Laplace transform, we needed to apply convolution theorem. So defining f of AB, just as we've been doing, by replacing b with AB, we would obtain this for the Laplace transform of that f of AB. So using this identity here, which is just taking the square root of this expression squared. So one could simplify this bunch of square roots to just this here. Then rationalizing, one would have this. So ideally, one would rationalize with the numerator by multiplying with this plus here. So one would have this very nice result. And then the next thing to do would just be to isolate s here by dividing by 2 times square root of 1 plus b squared. So now we want to evaluate the inverse Laplace transform. So to do that, as I said, we need the convolution theorem. And one application here is this here. So this is a convolution theorem when you take the inverse Laplace transform of the product of two functions, what you just have is the convolution of the Laplace transform of the individual functions. So here we define the convolution as this here. And one thing I would just like to mention was that we studied this convolution in functional analysis, and it has very nice properties because f could be a very bad function or a piecewise function, and G could be sufficiently smooth, and the convolution we saw that the convolution yields a better version of f. So we did this in approximation of the identity in functional analysis. So I found it rather nice because here it's just an application of the convolution theorem. So one could, this was the Laplace transform we arrived at. So writing this as 1 over s times this, we will just need to compute the inverse Laplace transform of 1 over s convolved with the inverse Laplace transform of this expression here. So, and elementarily, the inverse Laplace transform of 1 over s is 1. And then we just need to deal with this expression here. So we are just convolving with 1. So we will just return to the integral expression here and write this way. So 1 convolved with the inverse Laplace transform will just be the integral of 1 multiplied with, so 1 would just replace this. If 1 uses f of a to be 1, then this would always be 1. Then we'll just consider the inverse Laplace transform here by replacing the variable here with u if we want. So which was what we did. We just replaced the variable here, a, with u. So, and then the inverse Laplace transform of this expression is just this very nice exponent. So one would just need to integrate this. And integrating this leads to the error function. How? By replacing u with v squared. So one would get the error function. And you could just recall that the error function is just some constant with pi multiplied with 0 to a of the exponent of minus u squared du if you are integrating with respect to u. So just replacing u with maybe v squared, we just have the error function. And then this whole constant here, the term in the product here will just make us arrive at this error function here. So replacing b with b over a to get the original value of the integral, one would have this. And then you just rationalize because the expression in the theorem was a rationalized version. Then one would have this. So the nice thing to do here would be, as we've been doing, so it would just be to substitute the solution to the Pythagorean equation and then see what would happen next. So this is what happens. We derive an integral representation for the error function with the solution to the Pythagorean equation. We just replace a with v squared minus z squared, b with 2vz, and then we arrive at this result. So it's nice because everything here, let's look at the rationalized version. Everything here would cancel and just reduce to z by substituting the solution to the Pythagorean equation. So that's the nice thing. So we arrive at this expression for the error function with very mild conditions. So here we have this expression. We have that the integral from, this is a corollary from what we have earlier. We have that the integral from this, the integral of this is equal to this. Now it's rather difficult to compute this integral on its own because I don't know, maybe someone could do that. But then as an application of what we've been doing, one could just arrive at this integral from the result we've been considering earlier, or from the result we've had earlier on, pardon me. So by replacing b with u, So, okay. Yeah, so by replacing b with u in this integral, this is I1, if we could remember. So by replacing b with u in this integral and integrating both sides from u equals 0 to b, this is what we would obtain. So you could recall that at the beginning of this talk, we observed that this integral was actually a derivative of this integral. So now we are just doing the inverse, just integrating. So if you integrate, you would arrive at the sine function here. But we have a result for this already. So this would just, as I said here, we are replacing, let me write. So we are replacing b with u, and we want to integrate from 0 to b. So this is going to be u, and this is going to be from 0 to b here, and all these b's would be u. So we just have this integral here, and we would have this to be this here. But then we have this result. This is basically I3 or I2, one of the two, I3 or I2. So I can't remember the labeling. Okay, so, but then we've computed this. So it's either I3 or I2. So we just substitute the closed form for this, and then we would arrive at the integral. So that concludes it. So the beauty is that I don't know what one would use to compute this integral, and I don't think Mathematica can just compute this integral either. But with the theorems we've proved earlier, we can arrive at a result for that. So one would derive this expression for the error function similarly by replacing the variables with the solutions to the Pythagorean equation. So yeah, this whole integral would give the error function, which looks the integral looks rather complicated, but then the result is just the error function. And then this 1 over root 2 pi is quite classical, I would say. So this is the second part of the talk. So because the paper was divided into two sections. So the second part is rather short. So, and we start by proving this result. So actually, in the beginning of the work, the Iraqi guy actually he actually proved this result with some Fourier transform and stuff like this. But when we got a review from Integral Transforms and Special Functions Journal, so the review was that one could just apply Cauchy's integral formula to prove this, the famous Cauchy integral formula in complex analysis. So we had to ditch Ammar's result or Ammar's proof for this and just write it as a lemma of Cauchy. But if you check arXiv, in the first version of the paper we submitted, we kind of proved this using some Fourier transforms. It didn't just quite occur to us that one could use Cauchy integral formula to prove this, but easily one can do this, and it's rather short. So, and G is a nice function. By nice function, I mean that G is smooth. And so by nice function, I mean that G is smooth, and G of Z is some extension of G of X to the complex plane. So to the upper half of the complex plane. So one would obtain this result by Cauchy. So heuristically, one could see that this is some Laplace transform of the sine function. So heuristically, one would take the inverse Laplace transform here, and one would return an x here. If we could remember the Laplace transform of sine x or sine bx, or however we want to put it. So one would have this. So which would just be the Laplace transform of sine lambda x. So, and where the variable would be the x, like when you replace the usual s with x, and then you replace, and the constant in the sign is the lambda. So heuristically, one would just have this result, but then the proof was not done by heuristics. So I gave a detailed proof for this in the work. So a corollary of this is this here. So, and it's just a substitution of g of x with a suitable function. So I think either, if I could remember correctly, either x plus a or 1 over x plus a, 1 over square root of x plus a, one of these two. So when one replaces g of x with this, one arises at this result here. So that's the suitable function that I am referring to. So we have this result here, which I gave in the beginning of the talk. So we have this transform-based identity. So, and how to prove it was actually using some result of Srivastava and Urekli. They proved this identity where GL of x is the Laplace transform of GT. And then we apply this integral identity also. This integral identity here is just the famous Parseval identity for the Fourier sine transform. So, and then the condition on H and this imaginary part of g of Ix is that they are absolutely and square integrable. So this is the Parseval identity. So we just applied this, right? We just applied this identity here by replacing x with t and replacing h of x with exponential minus xt. So one would arrive at this result here. So one could easily compute the Fourier sine transform of exponential minus xt, so which gives this. So the next thing to do is to make appropriate substitution here. So you could recall that in that Srivastava formula, we had some Laplace transform. So by making appropriate substitutions, we arrive at this. So then switching the order of the integral and integrating over a, one would prove this identity here. So the next corollary is an application of the identity. So we can apply that identity to get this very nice result here. And the choice of the function is just 1 over x times the square root of x plus a. One would arrive at this identity here. So how to prove this? How to prove this integral? By choosing g of x to be 1 over x times the square root of x plus a, one would arrive at some Fourier, you would have to deal with some Fourier sine transform here. But this is the integral we want, then we just need to deal with this. But it's rather short. So the Fourier sine transform of this here, we can just take it from an example we had earlier on. So we already proved this from one of our examples. So I think that's just a few slides away. So this is what I'm talking about here. So we apply this corollary here, and then we just end up at the error function here. But then this is x to the power mu minus 1, which leads to this Mellin transform of this error function. So by evaluating the Mellin transform of this error function, one completes this proof. So the Mellin transform of that error function gives some of these gamma constants. And then this is just a very nice example from the previous corollary. Replacing a with 1 and mu with minus 1 over 4, one would have this integral here, which I found very nice. And that's the end of the talk. Thank you very much for your time. Thank you very much for listening.
Yeah, thank you very much for your very nice talk. I guess there might be some questions from the audience. Any questions? Please just go ahead and unmute yourself.
Hi, Abdul.
Atul?
Hi.
Hi. Nice talk.
Nice to see you.
Nice to see you too. Yeah, I had one question. If you go to the integral identity, that imaginary part of g of Ix or x to the mu dx.
Imaginary part of?
G of I.
Okay, yeah.
Yeah, that one. So is there any connection with Abel-Plana summation formula? Maybe you can explore if, because there also we take g of Ix minus g of minus Ix.
Yeah. So, oh, well,
I mean,
I do
it's
remember.
somewhat different because yours would be g of ix minus conjugate of g of ix, whereas there it is g of ix minus g of minus ix. But perhaps you can take a look whether there could be some connection.
Yeah, I could check that. I was trying to recall what you were saying. But I think the Abel planar formula, I think it's the
Mhm.
one used to get the integral representation for the Howard zeta function.
Exactly. Yes.
Okay. Well, I would check it. Yeah, I remember it has some g of ix and g of minus ix and
Right.
stuff
Right.
like that. Yeah, I could check it.
Sure. Okay. Thanks.
Thank you.
Okay. Any other questions? Yeah, maybe I can ask a simple question in that case.
Okay.
So there are very many formulas. How can you be sure that they have not been considered in the literature? What is the best way to find out about that? What do you usually do?
Usually I check Grashtan and Isaac,
Okay,
but for
Gradstein.
this,
Yeah.
yeah, yeah. But for this work, I checked all the papers on the application of the Laplace transform and I couldn't find them. Then I checked some integrals and I actually start with Mathematica, I would say. If Mathematica can
Mhm.
compute it, then it's probably been done somewhere. But if it cannot, then I have some bits of hope, I would say. So,
Okay.
and then I would just check. Usually, I check Grashtan and Isaac and some book of integrals and tables, stuff like this.
Mhm. I see. Yes. And then you checked probably with Victor Moll and other leading experts on integrals.
Yeah,
Yeah.
I haven't done that, but I could consider that in the future.
Okay.
I only did that with the one on the Malmsteen integral.
Okay. Yeah. The other paper. Yeah. Okay. Thank you. So any other questions? Then let's thank the speaker, maybe with a reaction. One can clap hands using Zoom. Yeah. Okay. And it was a pleasure